Okay, since this since there are so few of you here today to start class, I'm assuming that people are going to walk in late today. Um, Anyone else need to turn this test in? Uh, as far as, let's do this. If you've got something, just turn in right now and then talk to me after class if you about an extension. Okay. So I'd like to give everyone here for being at least being here on time and ready to go an opportunity for a bonus question. Okay. So here it is, and you got to work on it right now. And I'm only going to give you about 5 minutes to do it. All right. Hold on a second. Let's see who this is. Okay. That's it. Everyone else has to wait outside until we're done with this bonus question. All right. So I'll let you talk to each other about this, but let's say like not more than 3 people talking together, and don't be like, hey, yeah, this is the way we would do it or anything like that. Just, together quietly so everyone else can't hear you try and figure this out. Let's say that I wanted to, let's say I had 2 points sitting in 3-dimensional space. We'll take the point 4, 5, 6, very original, and the point -9, 2, 1. Right? Let's say you have 2 points in 3-dimensional space, right? And you want the equation, I want the equation of the plane equidistant from both points. So 2 points in space. Here, I'll make it real, hopefully this will be easy to see it. 2 points in space, one here, right? There's a plane right in the middle of the both of them. How would you get that? You got to wait for a minute, 5 minutes. Yeah, you can talk. What do you need for the equation of a plane? Normal vector and a point. Are you the only one here? Hmm? For those of you just coming in, y'all hang tight. Everyone else is working on a bonus question for being here on time. I know. But it's on the board if you're interested in looking at it. If you had them take home, it's right here. If anybody wants to talk about an extension on the take home, you'll have to talk to me after class. I might consider it, but you need to talk to me. For those of you working on that bonus, I'll give you about maybe 2 more minutes. Jose? Is Jose? These are the mini exams from last time. Daniel? Taylor? Jason Salinas? Cameron? I don't know why I looked around. John Doyle? Hmm. You know. Yeah, keep it. Anybody have that bonus yet? Do you have any idea what to do? Okay. What will the normal be? As the normal? That's it. Yeah, that's it. That's it. Yeah. So the midpoint's your point, and the vector connecting 2 points is your normal. That's it. Yeah. Did you guys have any idea of what you wanted to do with it? Okay, so what 14 is the direction? This will give you the equation of a line. That's the vector equation of the line between the 2 points. That doesn't give you the plane. Right? This is the vector equation of a line, but we want the equation of the plane between the 2 points. So Okay, let me talk about this problem, and let me tell you where it came from. I have a colleague of mine who also teaches um, Cal 3, and I guess they had just taken a test, and this was one of the test questions. And I wondered if my class would be able to handle that or not without any, having never done that problem before or seen it before. And I think a problem like this is pretty much kind of like a eureka kind of light bulb goes off, you see it, or you sit there forever and nothing happens. So if you have 2 points and you want the equation of plane between them, I'll use my little desk as the plane. If I have 2 points and I want that plane that's right between them equal distant, I just need a point, and I need for the equation of a plane, I need a point, and I need the normal of the plane. Well, the point of that plane, equidistance, is the midpoint of the points. Okay? So if I take the midpoint, how do you take midpoints, or how do you find a midpoint? Add the coordinates up, divide by 2. So if you take 4, add -9, you get -5. Divide by 2, -5 halves. And then you add 5 and 2 together, you get 7, divide by 2. And then you add 6 and 1 together, divide by 2. That's your midpoint. That's the point on the plane. Then what's a normal vector? The vector connecting those 2 points together. So that's it, right? That's all it is. So for everyone who was here, make sure, guys, that you'll turn that into me. Okay, so the reason I did that a little bit because I want to make sure everyone's here on time, especially on days when tests are due, because the test says on top of it, due at the beginning of class, and I don't think anyone here would be happy if someone walks in an hour late and I take their test, right? I mean, wouldn't you have liked to have had an extra hour to work on the test? So at some point, I can't take the test anymore. And on paper, it's the beginning of class. So you know what I'm saying? Like, we still have a few people that aren't here. What happens when they come in 15, 20 minutes late? Do you think that's fair for me to take their test? Maybe I should penalize them? How much? You know what I'm saying? So instead of having this gray area, be here on time, turn in the test as instructed, and we don't have issues. Also, on the last test, I took off if it wasn't stapled. That's part of the instructions. Staple your work. So if it's not stapled, you'll be penalized. All right, we are going to move on to 10.4 today. In 10.4, we're kind of a little ahead of the schedule right now, which isn't a bad thing. It's a good thing because we have a lot to do still in this course. And some of the topics coming up, we're going to want a little more time for. Now, your next test, your next mini exam, I don't have it. Well, I actually do have it. It's sitting on my desk. And I printed copies, and I was ready to hand it out. But then I thought, you know what? I'm going to just let them have one weekend where they don't have a mini test. And this is the weekend where you're not going to have it. And then Monday I'll have this next one for you, all right? This weekend? See? It's all working out. Oh, okay. Well, if you want it, you can have it. Yeah, if you want it, you can have it. It'll be due at the same time. This next one is actually not due until our midterm. I think it's 8 or 9 questions, but they're not. The problems that I'm giving you were not designed to be like take home necessarily. So they are very mechanical. It's very much just follow the rule or formula or whatever, and you get the answer, and it's done. That's what the midterm is going to be like. But not the next mini exam. All I'm saying is it's not like problem number 2 on the take-home that you just turned in, where you have to integrate and do all that, and then you have to figure out all these other things and make all these connections or do something from Cal 1. The one that you'll get next is going to be pretty much like problems in the book. I'm not sure. I see. I also haven't taken the whole test myself, so So if you want the exam early because you have a free weekend, you want to knock stuff out, that's fine. The only drawback is we really haven't done a whole lot of material, covered a lot of what's on that test. That's why I'm trying to move forward, because the more I get to, the sooner I get to it, the sooner you'll be able to start working on it. You can do problem number 1 right now, today. By the end of today, you'll be able to do problem number 1. Yeah. All right, let's talk about tangent planes. See how good my stuff works here. What is that? The bonus? Yeah, just bring it up here. So for tangent planes, if z equals f of xy is, what is z equals f of xy usually? It's a surface, right? And f has continuous partial derivatives. What do you think it means to say continuous? Well, it's not spelled correctly, obviously, but what do you think it means to say continuous partial derivatives? What did continuous mean? Like, no holes, no weird things happening, nice and smooth. Continuous partial derivatives, meaning that when you take the partial derivatives, those things are nice, well behaved. Then the equation of the plane, which is tangent to the surface at the point x naught, y naught, z naught, is given by this equation. So let's actually make sure that we see or recognize some things here. Y'all remember the equation of a plane, right? What's the general equation for a plane? A times x minus x naught plus b times y minus y naught plus c times z minus z naught, right? Equals 0. Well, doesn't that look a whole hell of a lot like the equation of a plane? The only difference is that instead of a, we have what? The partial of f with respect to x at x naught, y naught, which means at that specific point, you evaluate the partial derivative there, and that gives you the a that used to be part of, the a from the equation of plane. And then the partial of f with respect to y at x naught, y naught gives you the b of the plane equation. And then notice, what is c always when you're trying to find the equation of a tangent plane? The c is always -1. Okay? So this is nice. I add here at the bottom, notice that the normal of the tangent plane then is this. So that's the A, the B, and the C. Right? A, B, C right there. Y'all see that? Y'all see how this equation matches what we've seen before? So the essence of it is, basically, you can always find the equation of a tangent plane as long as you can take some partial derivatives and evaluate them. And that's what we'll do next. Ooh. Find the equation of plane which is tangent to the surface. Z equals f of xy equals 1/2 xy at the point 1, 2, 1. So what are the things we're going to need in order to compute this? Partial of f with respect to x, right? Let me figure that out first. What's partial of f with respect to x? 1/2 y. Now, what's the partial of f with respect to x at the point that we're given? Go back real quick and look at this right here. Aren't we going to need the a here in the beginning? Isn't it the partial of f with respect to x at the point x naught, y naught? Now x naught, y naught is just the x and y coordinates of the point in question, the point on the surface. So you have a surface, right? You have a point on it. At that point, there's some tangent plane. So we need the x and y coordinates in order to determine that first part of the plane. Does that help a little bit? Okay. So then let me ask you again. What's x naught for us? 1, and y naught is 2. So what happens if I plug in 1 for x and 2 for y into that partial we did up there? Well, x isn't even there, right? So plug 2 in there, what do you get? 1. Okay? Now that's the first part. Now let me do the next partial. I need partial of f with respect to y, which would be 1/2 x, wouldn't it? And then plug in 1, 2. And you get what this time? 1/2. So now that's all I need, right? I should be able to write the equation of the plane. So the equation of the plane will be what? 1, right? 1, x minus 1, then plus 1/2, y minus 2, then minus 1, it'll always be minus 1, right? And then z minus 1 equals 0. Now if I, clean this up a little bit, we have x minus 1 plus 1/2 y minus 1 minus z plus 1 equals 0. And we can start getting our constants, moving things around. Let's just get a final kind of nice cleaned up version. What do we have here? X plus 1/2 y minus z equals 1. That's good. That should be the equation of the plane. So if we were to graph this plane, right, graph that plane, then we would have, it should be touching that surface and be tangent to the surface. Now, I talked a little bit last time about tangent, right? I did. I was thinking about talking a little more about that. Like if you have a basketball, then if I were to talk about a tangent plane to that, think about a plane that would be balancing along the top like the North Pole, right? Or graduation hat. There you go. So that tangent plane, as you move around the ball, right, you'd have these tangent planes over. Well, every surface has something like that tangent plane. That's what we're looking for, and this is the equation of the tangent plane for that surface. Now, I'll copy this, and let's see if I have a visual for this. There we go. So this is the actual surface over here on the right. Okay, that's it right there. And I should have a plane. There's my green plane. And if I change the point, like right now, that's the tangent plane right there at the origin. See, this is my domain. I'm at 0, 0 for x and y, and that's giving me the plane that's passing through the surface at 0, 0. And now if I move that point around, that tangent plane will change, won't it? See how that tangent plane kind of just wraps itself around the other side, comes down this side. See how that works? Okay. Now the tangent plane that we found was right there. That was it. That's the exact answer that we just got. And I think it turns out it was x plus 1/2 y minus z equals 1, but I put it over here. So that's the equation. I think you would agree that that looks like the plane that's tangent to the surface at that point. Would you all agree? Looks pretty tangent. So it's a pretty simple formula, isn't it? Not a whole lot involved there. How about finding the equation of the plane which is tangent to the surface? Z equals f of x, y equals arctangent xy squared at the point 1, 1 pi over 4. Looks like a little more work, right? So let's start with the partial of f with respect to x. What is the derivative? Because this is going to be chain rule, right? What's derivative of arctan of something? Or arctan same as tan inverse, right? You remember that from Cal 2? Cal 1? Well, here, this might help. This might help. What's the antiderivative of 1 over 1 plus x squared? Arctangent, right? Arctan x. Or if you want, plus a constant, right? Do you remember that now from Cal 2? So if the antiderivative of 1 over 1 plus x squared is arctangent x, then the derivative of arctangent of x is 1 over 1 plus x squared. So for us, what's the x? It's really the xy squared, right? So the derivative of this will be 1 over 1 plus xy squared quantity squared, which is x squared y to the 4th, times now the chain rule. The derivative of what's inside the arctan with respect to x, which would be y squared. Which is really just y squared over 1 plus x squared y to the 4th. Now I'd like to evaluate it where? At 1, 1, right? So plug in 1, top and bottom, 1, 1, 1, 1, 1, you get 1/2. So that's the A. That's the A in the equation of the plane, right? X squared. The derivative, I think what you're asking is what happened to the x. When you take derivative what's inside here with respect to x, you treat y like a constant, right? So y squared is like a constant, so it may as well be 5. What's the derivative of 5x? Just 5. So whatever the constant is, the x goes away. Okay, let's do the next one. Now we need the partial of f with respect to y. It's pretty close to the same thing, except that at the tail end of it, we get what? Not quite just x, right? 2x, right? 2x, y. So that part's the same, but the derivative of the inside of this with respect to y would be 2xy. So partial f with respect to y is 2xy over 1 plus x squared y to the 4th. And then what's the partial of f with respect to y evaluated at 1, 1? 2 over 2, which is 1. That's it. I'm curious, because this may pop its head up at some point in time. What if I had not given you the pi over 4, and I just had told you at x1, y1? could you have recovered the pi over 4? Well, the pi over 4 is your z-coordinate, isn't it? And the z-coordinate comes from this. So if you plug 1, 1 in there, you get arctangent of 1. And arctangent of 1 is basically the angle that when you plug it into tangent, you get 1, and that's pi over 4. So you could have recovered pi over 4 without me actually giving you the pi over 4. Maybe that would at some time creep up on us. You could get it, though. Now, there are some other possible angles that could have given you that, but you know what I'm saying? Is that's not the only place you get 1, but yeah, I would have to give you some sort of domain restriction. All right, so the equation of the plane, though. It's partial of f with respect to x at 1, 1, that's 1/2, and then x minus 1, and then plus the partial of f with respect to y, which is 1 times y minus 1, and then always negative 1, z minus pi over 4 equals 0. And that'll be it. That all right? Questions? Hey, can you shut that door while you're there? Just kick that thing. Thank you. All right, I'm moving on. Oh, here's the picture of what we just did. This is the surface. Let me take that out of there. That's the surface for arctan. Kind of cool looking, huh? Huh. Interesting. So if you look at the tangent planes, I moved to some point around here, pop that tangent plane in there. Some weird stuff happening here. And the point we were interested in was 1, 1, right? Come on, there it is. That's exact. Whoa, no, it came off. Do it. Come on. There. That is exactly where we were talking about, right there. Okay? That's it. Pretty short section there. All right. 11.5. The chain rule. Everyone has 11.5, right? The notes on 11.5? I actually don't remember if I have 11.5 with me. So I might have to change it up here a little bit today. Let me see. Everyone have 11.5? It finishes out chapter 11. Yeah. Well, well, right now you can't do one yet until I finish this section. Yes, the rest of chapter 11. Yeah, as you'll see, the stuff we're going to head into here, like this is pretty straightforward, right? I mean, partial derivative, plug in some numbers, you got the equation plane. There's not a whole lot there. As you'll see, when we get to 11.7, 11.8, it's going to require quite a bit of work, what the problems we're going to be doing. So that's where a lot of the take-home test is. Midterm covers everything through 11, as far as I remember. Oh, no, you know what? I spared you. I actually, on the schedule, I saved 11.8 till after spring break. So through 11.7. That's a good thing. 11.8 is, it's called Lagrange multipliers, or I'm sorry, the Lagrange method, and it's very involved. So it's probably a good thing we're waiting on it. All right, since I don't have the notes in front of me, what I'm going to do is I'm going to open up good old OneNote here. Create a new page. But everyone here has the notes, right? Anyone need them out of the filing cabinet over there? So we're going to talk about chain rule. So the first note here says, recall that y equals f of x. We can find the derivative basically whenever we have y as a function of x. Let me give you an example of this. We have y equals x squared plus 6x minus 3. And they're asked to find dy dx. What dy dx meant for us was that we want to know the infinitesimal change in y as x changes infinitesimally. So if we have a curve out here, what we were really looking at is trying to find the change as you move from one point to the other, almost creating a right triangle, calling this kind of like a dx and a dy. It's not exactly that, but on the infinitesimal, that's really what's happening. It's like your rise over run in a basic college algebra class. It's rise over run. So if you change x a little bit, how much does y change by? Well, the key here is that y is completely determined by x. You give me an x, I can provide the y, right? You tell me a little bit about what happens to x, I can tell you then what happens to y. So there is a direct connection between the two variables, right? So it makes perfect sense to ask this question. If x changes, how much does y change? So, I mean, this is trivial, right? What's dy dx? It's just 2x plus 6, and we're done. So there's nothing there. But what I'd like for you to see is the way I drew this. I said here was y. Underneath it I put x, right? That's the page before this. So y was somehow determined by x. And therefore, since y was determined completely by x, I can say that I can find the derivative of y, or dy dx. Make sense? Okay, now let's move to the next note. What if, this is 11.3.2, what if y is a function of x and x is a function of t? So does that change the game? So now I have something like, I give one on the next page as an example. Y equals x squared, and x equals sine of t. You're asked to find dy dt. So what I want you to see here is, does it make sense to ask for dy dt? Well, can you determine y exactly? Can you tell me exactly what y is if all you know is t? Well, if I know what t is, right, then I know what x is. And if I know what x is, then I know what y is, right? So y is completely determined if I know what t is, right? Now I'll do this in a second, but let's look at a picture of this. Y is completely determined by t, but first, in order to know y, I first need to know what? X. And in order to know what x is, I need to know what t is. So that's my little picture. We're going to call these basically trees later, okay? We're going to call these trees because they're going to have more than one branch. It's going to split out. So going from y to x, right, is the one we just did before this. And so I can talk about dy dx, can't I? And then going from x to t, I can talk about dx dt. Does that make sense? So if I want to go all the way from y all the way down to t, which would be dy dt, the way I get there is I have to go dy dx first, then dx dt, and multiply those two results. And that's what chain rule was back in Cal 1. So if I want to know dy dt, I have to take dy dx and multiply it times dx dt. I'm trying to get you to see, though, the visual part of this tree, though. That to get from y to t down there, I have to go down that line and do the multiplication of those two derivatives. Follow? Now, what is dy dx? So focus your attention right here on the equation for y. What is the derivative of y with respect to x there? 2x. So I'm put underneath here, this is equal to 2x times, now what's dx dt? So come over to the other equation, x equals sine t. What's dx dt? Just cosine t, right? Cosine t. So over here next to this, I'm going to put cosine t. Now, is that correct? I mean, like, are we done? No, because we have x and t mixed together here, don't we? So all we do is replace the x with whatever x is. And what's x up there? Sine t. 2 sine t. And then I still have next to that cosine t. Now that's our derivative. This should be pretty much nothing surprisingly new to us yet. I want to show you something, though. What if I had in the very beginning of this problem, right, there's my problem up there, y is x squared, and x is sine t. Why don't I just go back up to that very beginning part, and why don't I just replace my x with sine t? Wouldn't I have had this? X is sine squared t? What's the derivative of this? What's dy dt? Well, chain rule, right? 2 comes out. 2 sine t times derivative of sine t is cosine t. So it's this, isn't it? Same thing? It's the same thing. I'm just showing you that as we progress here, another way of looking at what we've done in the past is to look at it with this diagram instead. It's going to help us keep things in order. Yeah. Hold on, 11. Let's see. We can find the derivative of y with respect to x. We can find it. Yes, that's supposed to say t. Thank you for pointing that out. Bottom of 11.52. Right there. It's supposed to say t there. The bottom of what? Oh, it's supposed to say dx dt. This is the first time I've used these notes. I'm making excuses for myself basically for not proofreading it. I did it correct here though. Like I said, it's more important. Okay, so let's look at something new now. I'm going to skip over the note, but I'm going to go to example 3. And I'll come back to the note in a second. What if we have z is equal to sine xy? Then let me ask you a question. What would it take for you to be able to determine z? What's that? Oh, yeah, I am. What would it take for you to be able to tell me what z is? you would have to tell me what x and y were, right? So z depends on two different variables. In the previous problem, to know what y was, we had to know x, but to know x, all we needed to know was t. So to know what y was, all we really needed was t. The previous problem to that, there was a direct connection, wasn't it? 1 to 1. One answer out if you just gave me the one in. This one, you have to give both in to get the one answer out, right? So it is not possible, right? It is not possible for me to tell you how much z changes by if all I'm willing to give you is x. Do you see what I'm saying? If I tell you how much x changes, you don't know how much z changes because you also need to know something about the y. It's very different than what we've done before. But what we can do is we can say, all right, since I'm not willing to hand you both, if I hand you the x and tell you the y is constant, then you can tell me how much the z changes, or vice versa. If I hold the x constant and let the y change, then you can tell me how much z changes by. And this is the idea of the partial derivative. So watch the way my picture looks. Z cannot be determined by one. It has to be determined by two different things, x and y. And x and y are just x and y. So, you know, there's no further branches coming down. It's just z is x and y. Now, can I actually determine dz dt? I'm asking you that. Well, kind of the d here, okay? The d, we've used that in Cal 1, right? Last class I introduced you to this kind of weird backwards-looking 6 del thing, right? That's reserved for partial derivatives. That lets you know you're holding something constant. So technically, it's not correct for me to write dz dt if I'm holding something constant. And I'm going to be holding in this case, if I want to know how z changes with respect to x, then I have to hold the y constant, don't I? So we don't use that. We use partial z with respect to x. That's the way I'll say it, partial of z with respect to x. And then the other way, I have what? Partial of z with respect to y. So with that said, there are two things possible in this problem. I can ask for two different partials, the partial of z with respect to x or the partial of z with respect to y. There are no other derivatives that I could find for this. Those are the only two out there. But there is not one derivative like the previous two examples, where there's just one possible derivative and that was it, and then you move on. This one has two. Just depends on what you're holding constant. So let's figure out what is the partial of z with respect to x. So what am I holding constant there? The y. So if I do that, what am I going to have to do to take that derivative? What's the rule I'm going to have to employ here? That's x sine xy, right? There's some chain rule, but there's also product rule. Right there, right in between the x sine xy. So I have product rule. That's the overwhelming thing I have to do first. Derivative of x is 1 times sine xy plus, what's derivative of sine of something? Cosine of it. What's derivative of the inside of the sine with respect to x? So treating the y as a constant. Just y. But then, finishing off product rule, times the x, that's times that x that was out here. Do y'all agree with that? Did I move through that too quickly? I have the derivative of the first one, derivative of x with respect to x is 1, times the second one, plus derivative of the second one is cosine xy times derivative of what's inside with respect to x, which is y. Done with that, come back, put in the second or the first function next to it. F prime g plus g prime f. So this equals sine xy plus xy cosine xy. That's it. Now the other partial, I do this whole problem again, but I treat my x's like constants. So do I have to do product rule? No. So it'll become x. Now I do have to take derivative of sine, don't I? So cosine xy. What's the derivative of xy with respect to y? So treating x like the constant. X. So you get x squared cosine xy. And we're done. Ah, that's a great. I'm glad you brought that. That's what I was saying earlier. There are two possible derivatives here. Those are two distinct, completely separated derivatives. We cannot combine them together and have it have any meaning because it goes back to the whole idea that z, to know what z was, required we knew x and y. If we hold both x and y constant, nothing's changing, and so everything's constant, and the derivative of a constant is 0, right? But if we hold one of them constant, allow the x to change, we have some idea of a derivative. It's called a partial derivative, but we do have some idea. If we hold the x constant and let the y change, then we have some other idea. But together, they don't have any meaning. Now, that's different than the one we did before. I'm so glad you brought that up because it's different than this one, right? For this one, because y was determined completely by t, in order to know how much y changed with respect to t, we found the derivative connecting these two, the derivative connecting these two, and we multiplied those derivatives together to give us our chain rule and to give us our final derivative. Yes? On this one, there is no, you have to go down the line, and those you can multiply together if there were more, but you can't do them if they're on separate branches. All right, next one. So I'm in 11.5.4, but I'm actually going to go to the example 4. I have z equals x sine xy, but then I'm also telling you x equals t squared plus 1. I'm telling you y equals natural log t. Now, I kind of give it away with what I say next here, but let's see if we can determine what derivatives are even possible with this. And I'll start by drawing the picture. Z depends on what? Initially, x and y. But x depends on what? T. And y depends on t. So ultimately, z depends on t, doesn't it? I mean, to note z, all I have to do is give a t. Once you give me a t, I can go up both these branches and get my way to z. Right? So z depends on only one thing. Follow that? Okay, now let's, through each of these lines, these branches off this tree, let's talk about the derivatives that go from branch to branch. So how about from z to x? That's a partial derivative because in order to, since z depends on two things, I would have to hold my y constant, wouldn't I? So I have partial z with respect to x. Now keep coming down that branch. How about x to t? That's a straight derivative. I always say straight derivative instead of partial so that you understand the difference. If I just say derivative, you might think I mean a partial or something. So I say straight derivative to mean the classical derivative from Cal 1. I say partial to be the one that you're holding the other variable as a constant. So this is going to be a straight derivative, dx dt. And then what about going down the other branch? Partial z respect to y and then dy dt. All right. So now what do you think the derivative will be? Like, what do you think is possible? We said z is completely determined by t, right? So I should be, since z is completely determined by t, the picture almost looks like this. Here, who cares what the hell's happening? And eventually t is what determines z, right? Now there's a bunch of crap happening, but ultimately z can be found if t changes. So if t changes a little bit, z is going to change a little bit too. So I should be able to find a single derivative for this. And it should be a straight classical derivative, dz dt. dz dt. But what do you think it's going to be comprised of? Let's see. dz dt will be equal to, do you think it's just multiply down this branch, this one times this one? Well, you actually have to come down this branch, and you have to pick up the other branch also. So let me come down the first branch. It'll be d partial z with respect to x times dx dt plus, now I go to the next branch and come down that branch. And that will be what? Partial z with respect to y times now dy dt. Do you all see this or not? Why could we not do that in the last problem? Why did I not just take the two and add the two together? Because they didn't all go back to the same variable t like these do. It was the x and y, and it stopped there, right? We didn't have this here. So we couldn't combine this together because they didn't ultimately come back to the same variable t. All right. Well, can you compute each of these four pieces? Can you take the partial of z with respect to x? That's up here. Can you take dx dt? That's derivative of this. Can you take partial z with respect to y? That's here. Dy dt is this. So should we do them? I'm trying to do them kind of fast. D z dt equals partial z with respect to x. Didn't we just do that? That was on the previous problem, wasn't it? Wasn't that sine xy plus xy cosine xy? Okay. And just because we like it, I'll color code these. That's that, right? That's the partial of z with respect to x. Now what's dx dt? 2t. All right. Plus, what's partial z with respect to y? Yeah, we did that one earlier too, right? X squared cosine xy. So that's this one. And then dy dt? 1 over t. That makes sense where all those come from? Now, is that our final answer? Unfortunately, no. We are not going to solve for t. What we're going to do is everywhere, because what we want, our z depends on t, right? That means that our final answer should have just t's in it. But you can replace every x in here with what? T squared plus 1. And every y in here with what? Natural log of t. And it would just look like a huge, ugly algebraic nightmare, but that's what you could do, right? So I come in here, I'd replace that x with t squared plus 1, 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 that one with t squared. And then I replace all my y's with natural log t, natural log t, natural log t, natural log t, then that expression would be your derivative. That's a great question. That's what it would be if I plugged it in the beginning. And you could take a derivative here, right? You could. The only problem would be you would have product rule right here, right? Product rule there. And then once you got to this one, you'd have chain rule with product inside of it. So that would be a bit of a mess. And, I mean, you could work it out. It would work. Yes, you would get the same answer. So imagine whatever I get here when I plug all the x, y, is the same answer you would get. So imagine how ugly that would be. This one, it's this. Yes, if it were an easier question, yes. But the whole idea behind the chain rule, if you remember from Cal 1, it was to help us take derivatives of more complicated expressions. So you take something complicated, use chain rule, and it's kind of like you work your way from your outside in sort of thing. This chain rule is to help us take very complicated functions that are dependent on other functions that might be dependent on other functions and somehow be able to spread the work out over this tree and keep everything organized rather than trying to get it all back to one master function and then differentiate that. I don't know if that helps, but kind of divide and conquer, sort of. And then you run into a problem like the next one, and that method may not work at all. Let's see. Yeah, go to case 2. So go to example 5. Oh, shit. The wheels are going to start coming off here pretty quick. X sine xy. And then we have, x is equal to t squared plus 4, that's an s, and y is equal to natural log st. That st is supposed to be inside the natural log like that. So let me talk about what derivatives are possible here. Z depends on what? Z depends on x and y. But what does x depend on? Two different things, t and s. T and s. Again for y, right? So will you be able to determine what z is if all you know is t? If all you know is t, there's no way you can tell me what z is. If all you know is s, you can't tell me what z is, right? So ultimately, we have a z up top, a bunch of crap happening, and then at the end of it, what? It turns out that we need t and s, right? So it'll be impossible for us to do straight derivatives, dz dt. That's not possible because we always have to do something with the s. So what's possible is partial z with respect to t and partial z with respect to s, but not a straight derivative. Do you understand the difference? Okay. So let's try and fill in the pieces of this tree. What about z to x? It's a partial. Partial z with respect to x. How about from x to t? Partial again, because there's an s there. Partial x with respect to t. Okay, what about the x to the s? Partial x with respect to s. All right, what about the z to the y? Partial z respect to y. How about y to t? Partial, right? Partial y with respect to t. I'm sorry, my Um, my partials are starting to look like weird twos. Apologize about that. Yeah. Y going to S is a partial again, right? So because we said that Z depends ultimately on two things, I said then there are only two derivatives possible. The two derivatives possible are partial of Z with respect to what? T, or partial of Z with respect to S. Those are the only two possible derivatives for this, right? It's like you cover up the whole tree and you say, hey, look, Z at the top depends ultimately on T and S. Since they're two different things, I can only find partials. So what do you think the partial of Z with respect to T is going to be? What do you think it's going to be? So I need to come down this way, like this on the tree, and then get myself down to the T, like that? Well, no, I'm looking at the yellow one over here. If I want the partial of Z with respect to T, I need to come down Z to X and then X to T, right? But I also have to go down the other branch, because the other branch also leads me to a T. So the yellow is actually the derivative dz dt, partial Z with respect to T. So you go down that first branch that gets you to T, then you go down the next branch that gets you to T. And you multiply as you go down the branch, multiply down the branches, but add branches up. So it'll look like this. You tell me. Partial Z respect to X times partial X respect to T plus partial Z respect to Y times partial Y respect to T. That's one possible derivative. Now the other one is partial Z with respect to S. And to do that one, I would have to make sure I start at Z and get myself all the way down to the S's. So I'd still have to come down this way, but now I split off to the right. And then I still have to come down to the one on the right, but now I need to split over. So what would it be here? Partial Z respect to X times partial X with respect to S plus partial Z respect to Y times partial Y respect to S. Now each one of those we could calculate, couldn't we? Like we could actually do these partial derivatives. You realize that that would take some work, right? Like just this first one right here. What's the partial of Z with respect to X? We just did that a while ago, didn't we? It was like sine xy plus xy cosine y. So that would be that. What's partial of x with respect to t? So come over here. Here's x. Partial x with respect to t, you hold the s constant, and so you get 2t. And then partial z with respect to y, we did that earlier. It was what, x squared cosine xy? And then partial y with respect to t, so we come over here. Derivative of natural log of something is 1 over it. Then the partial of that with respect to t would be s, wouldn't it? Sorry, this last one right here. Derivative of that is 1 over st times s. So the s's would cancel. You just get 1 over t. And then you could start plugging everything back in. It's a big mess, but that's the idea. That's all I'm here to show you for this one. Is Those are the two derivatives possible. Is this making any sense at all? So let's look at this wonderful 1156, the general case. The general case. This is a disaster. Look at this thing. Z. So let's say Z depends on, I don't know, n different variables. So instead of Z depending on X and Y, what if it was, this, this, and see what we start to do if we can have a lot of variables, we stop using X, Y, Z and things like that. We start subscripting our variables. Why do we do that? X1, X2, why do we start subscripting? X3. There's only so many letters, right? If you subscript, then you can have as many variables as you want. X1, X2, X3, all the way out to 4 quadrillion gajillions, whatever you want. You'll never run out. So I have n variables, right? So down each of those branches, what's possible? Down each of those branches. Partial derivatives, right? Partials, because to know one, you have to hold the others constant. But then what if each of those variables is dependent on m other variables? So I have T1, T2, all the way to Tm. And so is X2, and so is X3, and all of these are dependent on m variables. Now I stopped there, but imagine each of those could be dependent on however many variables you'd want also, right? But that's where the book stops, that's where I stop. So let's just try one of these, okay? Let's just look at one of these branches. If I wanted to know what does Z depend on ultimately, to know Z, don't you have to know T1, T2, all the way to Tm? You need to know all m of those T's. So there's no way I could talk about a straight derivative, right? dz dt. I could talk about a partial of Z with respect to any of those, right? So let's say I pick the second one. Then I could talk about the partial of Z with respect to T2, couldn't I? But what would it require for me to talk about that derivative? I'd have to go down this branch and then down that second branch, right? And then I have to go down this branch and then down that second branch. Down this one and down that branch. And go down every branch in the second branch on the T's. Wouldn't I? And then I'd have to add all those branches up. So what would this first branch be right here? This one on the left. It would be partial of Z with respect to X1 times partial of X1 with respect to T2 plus next branch. Partial Z with respect to X2, partial X2 with respect to T2 plus, keep going until I get to partial Z with respect to Xn, partial Xn with respect to T2. Now that's if we were coming down to the second T2, right? If I change this 2 right here to an I, then what would change here would be, everything here would be the same except this would be Ti, Ti, Ti. I think that's the formula you have on yours, right? So that's the general formula. Does that make sense? Oh, it does say T1 there. Yeah, fix that on the notes. The bottom, it's that first bottom left one right here. That should be at X1. All right. Let me ask you this. I'm going to draw a picture. Let's say we had that. What derivatives are possible? I mean, like in the previous problems we've done, we were always trying to find like how many derivatives even make sense to talk about. I'm not saying how many different branches and stuff. I'm just saying if you cover up all the crap, ultimately Z depends on what here? And since Z depends on T, it should be a straight derivative. That's the only thing possible here is a straight derivative. But how you actually get that straight derivative is by somehow combining all these branches together. See what I'm saying? So the only possibility in this picture is a dz dt. And what is it? It's down this branch and go pick up the t, right? Then go down this branch and pick up the t. Then go down this branch and pick up the t. And down this branch and pick up the t. And then down that branch, down. So basically every branch, right? And then as you go down the branches, you multiply. And as you put the branches together, you add, right? What would that first branch down the left be from Z to A? Straight or partial? It would be partial, right? Partial Z with respect to A. Then go down to the R. What would that be? Partial A with respect to R, and then down from R to T? Straight up, dr dt. So the first thing, if you were going to write this out, the first piece would be partial Z respect to A times partial A respect to R times dr dt. Plus, now I need to come down this side. And then go down, then down, and then down, and then down. See what I'm saying? I'm going to stop. I'm just trying to make sure you understand the idea here. All right, let's look at the next note. I'm actually going to skip this note. I'm as far as trying to explain it with my tree diagram here. I don't think that this tree diagram does. I think it'll confuse you more than it'll help you. Right? So instead, what I'm going to do is I'm going to point out on the page 11.5.7 continued. I want to point out the very last line here. Let's look at this whole thing here, I guess. I'm going to use this. I'm going to explain what this is, okay? I'm not just throwing this at you. I'm going to explain it. But that table in the front, the chart in front, the tree diagram, just don't worry about this, okay? Don't worry about that. So before I talk about implicit differentiation, I want to remind you of implicit differentiation from Cal 1. All right, so let's talk about implicit differentiation. Cal 1 stuff. If we had, let's say, x squared y plus sine x plus y equals y, and I said find dy dt, or dy dx, sorry, then traditionally what we like to do is try and solve for y, and then just take the derivative on both sides and One side of it's going to be dy dt, and the other one hopefully has just x's in it. But we saw in Cal 1 that if you can't solve for for y explicitly, then you have to use this other thing called implicit differentiation. And so what we did is we treated the equation like an equation, and we differentiated both sides with respect to x. Damn it, I changed that over there. I put, we want dy dx. So how would you do this back from Cal 1? How do I take the derivative of this first one right here? Product rule. So it would be 2x y plus x squared y prime, or you could say x squared dy dx, right? Y prime and dy dx pretty much meant the same thing in Cal 1. So that would be product rule there. Plus, then you'd have to take derivative of sine, which would be cosine x plus y. But then times the derivative of what was inside sine, what's derivative of x plus y with respect to x? 1 plus dy dx or y prime equals the right side, dy dx. And then what you do is you go and you try and solve for y prime, get y prime all by itself. Remember that? Okay, our goal now is to try and do the same sort of thing for functions of of 3 variables, or equations that involve 3 variables. So I'm going to go to example 6 here and put it up here, and then I'll show you how we're going to attack it. Yeah, I think it's example 6. I'll put it up here and you'll see it. X cubed plus y cubed plus z cubed plus 6xyz equals 1. So write that down, but then I want you to flip back to that page that I told you right after that chart. I said that we're going to ignore 1157, the next one, 1157 continued. I want you to look at that for a second, this box. What we have here is an equation with 3 variables, right? Because it has 3 variables, x, y, and z, in order to know what z is, what would you need to know? X and y, right? So there's no way that you're ever going to be able to tell me z unless I know both x and y. So it's impossible to find dz dx or dz dy because I have 2 things it depends on. So the only thing possible for me to ask for here would be partial z with respect to x or partial z with respect to y. Do y'all see that? The connection from what we've been doing? In the previous example that we just did, we only had x and y in the equation. So if I knew what x was, I could find y. If I knew y, I could find x. So the straight derivative made sense. So the way we will attack this is not the way we attacked the one earlier. We could, but it's tedious. We instead are going to use this formula that's at the bottom of this page. All right? And this is the formula for partial z with respect to x. It is equal to, I want you to read this carefully, negative partial capital F with respect to x over partial capital F with respect to z. The formula for the other one, partial z with respect to y, is on the next page. Okay? But what in the heck is capital F? You see? Like, what's capital F? So what we have to do before we can begin this problem is we have to take the original equation, move everything to one side, and make it equal to 0. So I must, and this is important because when you get to a test, I may have x's and y's on both sides of the equation. You have to move everything to one side. So if I move everything to one side right now, get x cubed plus y cubed plus z cubed plus 6xyz minus 1 equal 0. This left side over here, I'm going to call capital F of xyz. In other words, it is a function of how many variables? 3. And so in my formula over here on the right side that I boxed, I need to know two things. The partial of f with respect to x. What does that mean? We're going to take the partial of this left side, basically. We're going to treat x like our variable, and we're going to treat y and z like they're constants. Y and z at the same time like they're constants. So what is the derivative of x cubed? 3x squared. What is the derivative of y cubed? 0. What's the derivative of z cubed? 0. What's the derivative of 6xyz? 6yz. What's the derivative of negative 1? 0. So we're done. We're done. We've got the top of this. Okay, we got the top of this. Now what's the bottom? It's the partial of f with respect to z. So now I'm going to go through that whole thing again. I'm going to treat my z like a variable. I'm going to treat x and y's like constants. So what would this derivative be? 3z squared plus 6xy, and that's it. And now just make a fraction out of those and put a negative on top. Did I not bring my book? Does anybody have their book by chance that I could borrow real quick? I want to tell you where this is in the book, because they actually derive the formula for this. It's on page 655. If you want to go through and see where they come up with this formula, then you can look there. Thank you. So our final answer is partial z with respect to x is equal to negative. Can we reduce any of that? Let's see. When we put those together, we'll be able to factor 3 out, won't we? And cancel. So we'll have x squared plus 2yz over z squared plus 3xy. 2, yes, thank you. 2xy. Yeah, but the formula would change. That would be different. Well, no, the whole thing would, because if you have to see how they derive the formula, because the way the formula was derived, that final answer over here, the way that that's derived, it's just the way certain things cancel out and move on the equation. Look through. That's why I want to point out it's on 655. If you extend this to 4 variables, that formula won't be the same. So, like imagine it was x, y, z, and t. Then this right here would be possible, but it would not be that. You would still have to account for that partial with respect to t somewhere in the formula. This is as far as we're going to go with it. All right, let's see if there's anything else here. I'm not going to do the other one. Okay, so I'm not going to do partial z with respect to y because the formula is right there. Hey, that's 11.6. Are we happy? I mean, that's 11.5. Yeah, I didn't put homework on there. Let me send it in an email. Okay, I'll go to my office right now. I'll make sure I pick the right sorts of things to look at. I think we'll end a little early. I don't want to start directional derivative. It's really not time, but not enough time to get into it. All right.